we're going to evaluate the same integral as we did using the trapezoid rule, but this time we're going to use the Simpsons rule. It uses just a slightly different formula in this case. Some coefficients change, but again, the way we're going to go about computing the result, it's using the graphing calculator by recalling the function using the y bars function on the calculator. So let's go for it. So let me do, okay. On the graphing calculator, I'm just going to input the quantity inside of the brackets. That is going to be, okay, let me clear all this. Okay, so vars, y bars, function, y1, open parentheses to evaluate it at the lower limit of 1, close parentheses. Now be careful. The second term has a 4 as a coefficient, right? So you want to be careful with that. So plus 4 times, okay, vars, y bars, function y sub 1, open parentheses to evaluate it at 1.5, and then close parentheses. The next one, recall that it alternates between 4s and 2, so that'll be plus 2 times vars, y bars, function y1, open parentheses to evaluate this at 2, which is the x sub 2. Now let's do the x sub 3. So that is going to be plus 4 times vars, y bars, function y sub 1, open parentheses to evaluate it at 2.5. And again, go back to the paper, go back to the notes to check that we are about to evaluate the very last result, which is the f of b, which in this case is f of 3. It doesn't look like a 3. So plus vars, y bars, function y1, open parentheses to evaluate it at 3. Close parentheses and simply click enter. That's going to give us a 52, 81, 866. I'm gonna keep 5 decimals for now. So that'll be s sub 4 equals to 1/6 times the quantity, what's that? 52, 81, 866. 0.81, 866. And then this is approximately, so divide this in this case by 6. Final answer 8.88031. So that'll be 8.8031. Let's compare with the trapezoid rule. What did we get for that? 8.8967. I mean, we still got the 8, I mean 8.8, 8.8. However, looks like using trapezoid rule could be the trapezoid rule. It's actually an overestimate, while the Simpsons rule is could be a little bit of an underestimate. How about we summarize the results? Okay, so summary only for the integral from 1 to 3 of the cube root of x plus x to the 6 dx. Number 1, using trapezoids, using the trapezoid rule. What did that give us? That gave us 8.8967. 8967 using Simpsons rule. That gave us 8.8031. All right, and lastly, using FNINT, actually finding the actual value of the integral using the graphing calculator. That's the actual result. So let's go to FNINT. That'll be, okay, math. Let's go to number 9 for FNINT. That's going to give us the integral from 1 to 3 of, okay, here is where we input the function math. Number 4 for the cube root. For the cube root, that's actually x plus x raised to the 6th power dx. And click enter. 8.0252, 8.8025. And as we can see, well, it looks like the result we got out of the Simpsons rule, it's the closest to the actual value of the integral. I mean, don't get me wrong, the trapezoid rule did a good job, and I'm pretty sure that if we computed the left endpoint, the right endpoint, or the midpoint using Riemann sums, that is areas of rectangles, that would have given us a so crazy overestimate, a very inaccurate underestimate, and well, for midpoints, we would have gotten something close to the trapezoid rule, but still a little underestimated, I'm pretty sure. So again, Simpson's rule for sure improves the approximation to the actual value by a lot. I mean, from 0031 to 0025, there's a difference of, what is that? 0006, right?